Homework 3, problem 6, find the potential difference between a point on the edge and a point in the center for the coaxial system shown below. The coaxial system, I didn't write it all down here, but we have a uniform charge density in a solid cylinder of radius A, and then we have a cylindrical shell of radius B with the opposite surface charge density such that we have a neutral system in total. In order to do this, we're going to use our typical method so far, which we've used for problems 4 and 5. We're going to use Gauss's law and use that to find E. And then we're going to use, or we're going to integrate, and we're going to find V using that integral. And so V is from reference point to the point we're interested in, dl dot E, and negative sign. Okay, we have a cylindrically symmetric system, so the Gauss's law that we use in this case is going to be a cylinder. The height of the cylinder we're going to say is L, and the radius of the cylinder we're going to say is S. The integral form of Gauss's law is that the flux of the electric field through the sides of the volume that we have with an epsilon naught equals to the total charge enclosed, which is a volume integral, right, of our charge density. We have, in this case, we see that we're never going to enclose the charge from the outer cylinder, so we don't have to consider it. So we only need to look at two regions, inside radius A and outside radius A. For the left-hand side, we're easy, right, because we're going to make the same assumption that through symmetry, E is only in the S hat direction, and our normals that we're looking at on the top and bottom, the normal is plus or minus Z hat, so n hat dot E is going to be 0 on the top and bottom, and on the side, the normal luckily is in the S hat direction, and so that's simply going to give us the E that we have here. Furthermore, since we have some cylindrical symmetry, if we rotate the entire system about this axis, it looks the same. That means E can't depend upon the azimuthal coordinate. Therefore, this is just the surface area of the edge of the cylinder, which is 2 pi s, that's their circumference, times L, the height of the cylinder, and then epsilon naught, this E here. Over here, we have to worry about the two regions. If we're inside the, if S is less than A, then the charge enclosed is going to be the volume of the cylinder that we have. That's pi S squared times its height, L, and this will be times rho naught. And this is for S less than A, and for S greater than A, it's just the volume of this charge cylinder, so pi A squared times L times rho naught. This is for S greater than A. Combining these, we're going to get that the electric field in these two regions is going to be the pi's will cancel, the L's will cancel. We're going to get that E is equal to rho naught over 2 epsilon naught. And we're going to get an S hat for S less than A, and A squared over S hat for S greater than A. Okay. That is the electric field. The potential difference then, delta V, is going to be the minus the integral from 0 to radius B of ds prime of this electric field right here, this E. which we're going to break into two parts, minus the integral from 0 to a ds prime rho naught over 2 epsilon naught of s prime, that's for s less than a, minus the integral from a to b ds prime rho naught over 2 epsilon naught a squared over s prime. So doing these are two fairly quick evaluations. So delta v is going to give, let's pull the rho naught over 2 epsilon naught out front. For this term, minus rho naught over 2 epsilon naught out front. For this term, we're going to get the integral of s ds is equal to, excuse me, the integral of s ds is 1/2 s squared, so it'll be 1/2 a squared, 1/2 a squared, and then plus the integral of ds over s is log, so this is log of b over a. And so that is the potential difference between a point on the center and a point on the edge.